And welcome back to the second part of the video. Still in chapter 1.1 reactions rate. So let's look at rate law in this video. It's also known as the rate equation. So this refers to an equation that relate the rate of reactions to the rate constant and the concentrations of reactant which raised to some power. It's quite difficult to understand a sentence. Let's look at the equation. So this equation refers to your rate law. So rate of reactions relate to the rate constant and the concentrations of reactant A and B, which raise to the power m and n. So this K refers to our rate constant, m refers to the order of reaction with respect to A, which is your power towards A. And then the other one, the n, is the order of reaction with respect to B. So m plus n, adding up both of your power, equals to the overall order of reaction. So let's look at the terms. What is the rate constant referred to? What is the order of reactions referred to? So first of all, rate constant, which we're using a small letter k. This rate constant, their unit varies, which means for different order of reaction, they have different units. Okay, so units of K depends on overall order of reaction. And we can derive them mathematically, or you can derive it on your own. So I will teach you in the later slides. The second term over here is the order of reaction. So order of reaction in this case shows how the reaction rate is affected by a reaction concentration. All right, so this one is the power. Okay, this order of reaction is the power. If you remember just now, we have the m and n. Okay, m with respect to A, n with respect to B. So they refer to the power of reactant concentration in the rate law. And also, order of reactant does not relate to stoichiometric coefficient. This sentence means that even you have a balanced equation, the order is not the same as the stoichiometric coefficient. They are not the same. Okay, it means that order cannot be predicted from stoichiometry and it must be determined experimentally. We have some different method for you to identify to determine the order of reaction in the later example. The last terms over here, we have our half-life. So half-life refers to the time required for the concentrations of a reactant to reduce to half of its initial concentration. In this case, it means that if initially I have a concentration of 100 molar, okay, so this half-life is the time required, okay, for the initial concentrations to reduce to its half of its initial. So half of it, the initial concentration equals to 50 molar. So this one is the first half-life. Okay, and then we can still carry on. So if I continue to my second half-life, so initial concentration will reduce to its half. So 50, half of it, it becomes 25 molar. So this will be the time taken for a reactant to reduce from 50 to 25. If I still want to carry on, the third half-life is the time taken to reduce from 25 to 12.5 molar. All right, so next we want to look at overall order of reactions, and we have three orders altogether, which is zero order, first order, and second order. So first of all, zero order. Okay, this zero order refers to the overall order reactions. So normally, if you have zero order, it refers to some reactions which we use metal as the catalyst. So metal catalyzed reactions. For example, the metal catalyst will be iron, nickel, platinum, etc. Okay, so for zero order of reaction, the reactions rate is independent on the reactant concentrations. Why do we say so? Let's look at the rate law. So for zero order, the rate law is like this. Rate equals to K constant. Okay, so in your rate law, there is no concentrations of any reactant. Or in another words, if you want to see if I represent one of the reactants is raised to the power 0, it still equals to 1. Okay, so in simple words, we say the rate law equals to only the K constant, okay, the rate constant. So the concentrations will not affect the reactions rate. So for the unit of K equals to the rate itself, okay, which the rate has the unit of molar per second, molar per minute, and etc. Depend what is the units of your time. So in order to plot a graph of rate against concentrations, so since we know that the reactions rate is independent on the concentration, okay, therefore, no matter how we adjust the concentration, we increase the concentration or we decrease it, the rate will still maintain. Okay, the rate remains the same. Next, for zero order 2, we have another formula which we call as the integrated rate equations. So integrated rate equations we have for zero order, first order, second order, they are all different and we need to memorize this formula. So we have the concentrations. So we have concentration A at initial, which refer to this 0 means when time equals to 0, yeah, minus concentrations after certain time, which is the concentration at time t, equals to kT. So K is the rate constant, T is the time. So we are going to use this integrated rate equation for most of our calculation. We'll show it in the example questions later on. And for this integrated rate equations, we can also use it to plot a graph. Okay, so we try to rearrange so that we make the concentration at time t, the subject, which is your y-axis, equals to negative kT plus A naught. Okay, concentration initial. So we can make this equation, we rearrange this equation so we can get y equal to mx plus c. So y-axis is your concentrations at time t. Okay, the gradient equals to the negative rate constant. And then your x-axis is your time taken. And the intercept is the initial concentration. So this is the graph for concentrations against time t for zero order. So you can see we have our y-axis, concentrations A, and then our x-axis is the time taken. And then with our intercept, we have the A naught, and then the gradient equals to negative K. So this is for zero order using integrated rate equation. Last one, let's look at the half-life for our zero order. We have a formula of half-life T half equals to initial concentrations of reactant A over 2K. So in this case, we can see from its formula, half-life is directly proportional to A naught. Okay, this means that when our initial concentration decreases, the half-life decreases as well. So we have our first half-life is greater than the second half-life. Or in a simple words, we can say the half-life decreases over time. All right, so we look at the graph of concentration A against time. So when you plot a graph, you will see a linear graph. Okay, so remember that the half-life is the time taken when the concentration reduced to the half of its initial. So this is original initial concentration, and then when it reduced to the half, and then this is what we call as the first half-life. Okay, this is the first half-life. So I will label it over here. You may label it and complete your table in your notes. And then the second half-life is when you further reduce the concentrations to the half of its initial concentration. So the second half-life initial concentration will be this one. So half of it, it becomes 1/4 of the initial concentration. And then this will be your second half-life. Okay, remember we are starting from the point where we stop for the first half-life because now we are taking this one as the initial concentration. So when you reduce to half of it, this distance will be your second half-life. So you can see that the half-life decreases with time, where in which we say the second half-life is smaller than the first half-life. Okay, if you can't take for the ratio, then maybe we can take for the value. So let's say the initial value is 1.0. Reduced to half of it, it becomes 0.5. Further reduced to another half of the concentration, it becomes 0.25 and etc. Okay, so this is the patterns for our zero order. You may want to jot down some of the information into your table. Okay, so very important now, the patterns over here for zero order half-life decreases over time. So next, let's look at first order of reactions. So normally, if a reaction or a question mentions about radioactive substances, for example, uranium, or it's say a radioactive decay substance, it refers to a first order reactions. So take notes over here. Radioactive reaction is first order. So for this first order reactions, the reaction rate is directly proportional to the reactant concentrations. It means that when we double the concentration, we will double the rate. It increases directly proportional. If you increase the concentration by 3 times, the rate will increase by 3 times. So it all refers to your rate law. So as you can see over here, rate equals to K times the concentrations of A raised to power 1. So this is first order. Now remember, the power is the order of reaction. So if your power is equals to 1, that means your order is first order. Okay, so the unit for this first order, unit of K is per second, per minute, per day, per year, and etc. Okay, so if you look at the rate law over here, rate equals to Ka raised to power 1. So we know the rate, you have the unit of molar per second. Okay, in order to know what is the unit of K, we need to derive it mathematically. So the concentration, we have the unit M. Okay, therefore, if you simplify this units, K bring over equals to M as -1 over M. So cancel off the concentrations, get you per second. The unit of K is per second. So using this rate law, the graph look this way. So rate, okay, against concentration. So this one will be your y-axis. This one will be your gradient. This one will be your x-axis. So y-axis is rate against concentration. So the gradient equals to your rate constant. So according to this graph, we will see that the rate is directly proportional to the concentration. So first order integrated rate equation, it can represent by 2 ways. First of all, you have ln A0 minus ln AT equals to KT. Or we simplify using one ln only. Okay, so ln A0 on the top, AT on the bottom equals to KT. So normally, if you want to do calculation, we will use the second one to do the calculation. And then the first formula normally will be used for the graph. Okay, so we try to rearrange this integrated rate law to make it ln AT the y-axis. So you have minus KT plus ln A0. So against to plot the graph, you need your y-axis, your gradient, your x-axis, and then intersect C. So here is the graph of ln A against time. So y-axis, x-axis, your intersect C, and then the gradient equals to -K. And lastly, for first order, the half-life equals to ln 2 over K. So in this formula of half-life for first order, we can see that the half-life is independent to the concentration. Okay, so that means that Doesn't matter what is your initial concentrations, your half-life remains constant over time. Okay, so refer to this graph. If you want to interpret your half-life, our graph is always the concentrations against time. Okay, concentrations against time. So when you plot the graph, you will see the first half-life is when it reduced to half of it. So this is your T half, the first half-life. And then the second half-life start from the place where you stop for the first half-life. So this is your second half-life. You can say that the first half-life and the second half-life is about the same. All right, so take notes on the train. For first order, the half-life remains the same over the time. And second order, for second order, the reaction rate is directly proportional to the square of reactant concentration. So this one refers to the rate law, yeah? So if you look at the rate law, rate equals to K and then concentration A raised to power 2. So directly proportional to the square of reactant concentration. So it means that if you double the concentrations of A, the rate becomes quadruples, or it increased by 4 times. So for this rate law, it can also write it this way. Okay, K, A, and B. So even if you have two different reactants, it's still considered as second order because concentration A raised to power 1, B raised to power 1. So the overall order also second order. Okay, so this second order, first order, zero order, we refer to the overall order of reaction. Alright, so the unit of K is per molar per second. So if you look at the rate law, so the rate you have the unit molar per second. Okay, and then we want to figure out how to get the unit of K. So in this case, concentrations A raised to power 2. So you have your M squared. Okay, so trying to rearrange back your formula so that we can get the units for K. So MS minus 1 divided by M squared. So in this case, which give you per molar per second. Okay, so unit of K for second order is per molar per second. If you want to use, we know that molar can be also used mole per liter or maybe mole per dmq. This one can be used as well. So if you want to use mole per liter, so what we want to do is we just substitute mole per liter into your formula. So it becomes per mole liter per second. So this will be a formula. So be really careful if you got the formula mole per liter or mole per dmq in your questions. All right. So the graph using rate law, rate against concentrations. So this is directly proportional, and you can see it increase, and you can see that it increased exponentially. So let's say if I want to double the concentrations of my reactant A. So what I want to do is to double the concentrations. I put 2A and then both raised to power 2. So if you open up the bracket, 2 squared becomes 4 and then concentration A squared. So we know that the rate increased by 4 times. Okay, the rate increased by 4 times. Similarly, if I increase the concentrations by 3 times, okay, increase the concentrations A by 3 times, so 3 squared give you 9, so the rate of reaction increased by 9 times. And if I increase by 4 times, 4 squared give you 16, so the rate of reactions increased by 16, and so on. So this is for second order reactions. The integrated rate law of our second order, it will be 1 over concentration at time T minus 1 over concentrations at time 0 equals to KT. So to rearrange so that we can plot the graph, so it becomes 1 over AT equals to KT plus 1 over A naught. Not miss initial, yeah? So the graph it looks this way. So 1 over AT is your y-axis, and then the intercept is 1 over A naught, and then your x-axis is your time t. So the gradients over here, m equals to k, a positive slope. And lastly, for our half-life, the half-life for second order, t half equals to 1 over k the initial concentration. So in this case, if your initial concentration decreases, your half-life increases. So you can see that the half-life for 3 different order, they have different patterns. So for this second order, half-life is inversely proportional to the initial concentration. So the first half-life will be smaller than the second half-life. And our half-life for second order increases over time. So looking at the graph, so when you plot the graph of concentrations against time, you will see the first half-life, all right, is smaller than the second half-life. So this is the trend for second order. The second half-life is bigger or longer than your first half-life. All right, so remember the trend for second order, the half-life increases over time. All right, so let's look at your questions 1. Determine the order of reactions for the reactions given below. So in this case, you are given a balance equation and you are given a rate law or rate equation. So order of reaction, if you got already the rate law, you will determine from your rate law itself. Okay, so from the rate law, the order of reactions for the reactant H2O2 is first order as that it raised to power 1. So this is first order reaction. Whereas for your iodide ion, it also raised to power 1. So for iodide ion, it's also first order. However, inside your rate law, that doesn't have any H+, but in your balance equation, there is another reactant which is your H+. So we can know that this H+, it raised to power 0. As anything raised to power 0 equals to 1. Therefore, for reactant H+, the order is 0. So it is a 0 order for H+. So in this case, the overall order of reactions equals to second order. So we just add it up together to get our overall order of reaction. So for the same questions, determine what happens to the reactions rate if each of the following changes occur. So first one, doubling the concentrations of H2O2. So using back your rate law equation, so rate equals to K and then H2O2 and then I2. And then I minus. Okay, so doubling the concentration of H2O2, that means we increase the concentrations by two times. So times 2 H2O2, and then nothing mentioned about I minus, right? So we just maintain. So in this case, we just bring over this value to the front of your formula. So it becomes 2 times K H2O2 and then I2. So if you look at the numbers over here, we can know that the rate increased by 2 times. So the rate increased by 2 times. So for B, threefold the concentration of H2O2 and I minus. Threefold, that means increased by 3 times. So in this case, rate equals to K times 3 times of the H2O2 times 3 times of the iodide ion. So therefore, bring over the numbers. 3 times 3 give you 9. 9K H2O2 I minus. Okay, so this rate the reactions rate increases by 9 times. Let's see if you have the concentrations of H+. Since in the rate law, H+, you have a 0 order. So inside your rate law, it doesn't have any H+. Therefore, in this case, the rates will remain constant. Remains unchanged, remain constant, and it doesn't affect the rate. No matter how you adjust the concentrations of H+, which is a 0 order. Example questions given here, we have iodine atoms, which is I, combine to form a molecular iodine gas, which is I2. Iodine gas, you have a formula I2. Yeah, iodine atom refer to a single I. So at 35 degrees Celsius, the rate constant given here is 7.0 times 10 to the power of 9. And the unit, this one refers to rate constant, which is the K. So remember that unit of K is different from different order of reaction. So in this case, if you got per molar per second. This one refers to a second order reaction. So recall the unit for rate constant. If you have zero order reactions, the unit of K is molar per second. If you have first order of reactions, the rate constant K, you have a unit of per second. And if you have a second order, you have a unit of per molar per second. Given here is the initial concentrations of I is 0.086 molar. Determine the concentrations after 2 minutes. Be very careful of the unit since in your rate constant you are given a per second. So that means the time will be in seconds. So we need to convert this 2 minutes into seconds. So times equals to 2 times 60 seconds equals to 120 second. Make sure that your unit is the same. So second, convert into second. So for this second order, in order to know the final concentrations, we need to choose the formula for second order. So integrated rate equation for second order. Okay, so I at time t. So remember in your equation we have A. So this A is general. Now we have a specific, which is a reactant iodine atoms. So 1 over IT minus 1 over I naught equals to KT. So just substitute the value into this integrated rate equation. So 1 over IT minus 1 over initial concentrations given in the question 0.086 equals to the rate constant 7 times 10 to the power of 9 and the time taken 120 seconds. Solve your calculation, so you will eventually get your 1 over IT equals to 8.4 times 10 to the power of 11. Don't forget to find the concentrations of I, which is equals to 1.19 times 10 to the power of negative 12 concentrations with the unit molar. Okay, so this is your final answer. So formula accordingly. So integrated rate equation is to use for you to do calculation according to the overall order of reactions. For questions number 3 and question number 4, please try it first and we are going to discuss during our tutorial sessions.